So this is Sabahuddin Ahmed from Pakistan, and I will be presenting my solution to the problem number 9, graphite lamp. So, oops. Yeah. So now if we, start with the problem statement, and I will just, turn on this video for here. We have to devise the most energy efficient lamp possible using the graphite rod from a pencil. Investigate how the intensity and duration of the light depends on the hardness of the graphite and other relevant parameters. The other relevant parameters that we will be considering will be length, distance, and resistance. And you can clearly see from the image inserted, which we performed in our experiments, that we were able to, achieve this phenomena of, getting the glow from the graphite rod. So let's move. It's just a simple introduction of what graphite pencils are made of. It's a mixture of graphite and clay, and graphite is delocalized electrons, so they conduct electricity. So what's the dependence of hardness variation? Because we know that the graphite is made up of graphite. The graphite rod, pencil rod, is made up of graphite and clay. And the hardness variation, it depends on the amount of clay. So as the amount of clay increases, we have a increase in hardness. And due to this higher proportion of graphite content, it's inversely related, and you can clearly see from the graph inserted on the right side. This is the approximate composition of the graphite and clay within the pencil rod, and the reference has been inserted below. So as we move from 9H to 8B, the hardness is decreasing due to the decrease in clay amount. So with the phenomena behind this whole heating effect, or this glow effect, is Joule heating, which is the production of heat by passing electrical current through a conductor. And the equation is given on the screen: Q is equal to I square RT. When current flows through the graphite, it begins to heat up, and the electrical energy is then converted to thermal energy, and then that is results in a glow, which we can clearly see through the visible light. Now, in the intensity relation is that as the higher current or higher power is passing through the pencil rod, the brightness will increase. So its intensity is directly proportional to current, and then intensity is also directly proportional to resistance. Since the harder the graphite rod, the more the resistance, and the brighter will be the glow of the graphite rod. Now, the setup that we use for performing our experiment is this. As you can see, we use a DC power supply with a maximum current 5.26 ampere and a maximum voltage of 18 volts, 18.88 volts, and then we use a silicon photodetector, to check the variation of intensity, which gave results in millivolts, and we were able to get those results on the voltmeter. And we used a black box since the silicon photodetector is highly sensitive. So to avoid the saturation value. So to avoid the saturation value, to avoid the saturation value, we had to enclose it inside a particular system, so that it just shows the variation of our lamp. Okay, so we used experimental variations that we used for graphite hardness were 2H to 8B, 12 different variations for hardness, and 9 different variations for length, 17.6 to 1.6, and then 4 different variations for diameter as they were available. So in terms of experimental measurements, we measured light intensity, we measured the duration of the transient state while changing the current, we measured the duration of the glow, and we measured the duration of the glow at the maximum current as soon as it was reached. And I will move towards the results, and then you can clearly better see what I mean by this 2 different duration of glows. So variation of resistance. Now, resistance is directly proportional to length, and it's inversely proportional to area. And we will be ignoring the temperature dependence. It was difficult to include this particular part in our experiments. And then resistance is directly proportional to hardness. So this is the variation of resistance. And then our experimental observation for our experiments, that we were able to observe that the resistance was directly proportional to the length for our pencil rods, and resistance was directly proportional to the hardness of the pencil rod. Now, please don't get confused from the graphs, since it has a decreasing gradient, but the hardness is decreasing from left to right side. Okay, so in terms of now towards our results for the experiment, in terms of variation in hardness, we were able to observe a very high intensity for the pencil type HB, and the first maxima coincides with the maximum at the point where we reach the maximum current from our DC power supply. So before that maxima, we have a transient state, and after that, there's a steady state in which the intensity gradually decreases while keeping the current constant, and that coincides with also a change of fluctuation in the voltage as well. Okay, so this was by the other hardness types had a very low intensity as compared to HP. So since we were going towards the maximum part unit intensity, so I will be considering HP for this particular results as the main result for this part. In terms of a more conclusive summary of this, we were able to observe the maximum intensity at this point, and there was a higher glow time for HP as well. With the higher, I mean, the glow time is not from the start of the current to the end of the glow. It's the duration where the intensity is at a very higher value as compared to the remaining part, initial and the final stage. And then in terms of variation in length, we were able to, get a high peak. It's the same phenomena, the same pattern as before, but we were, it's a continuous graph. So we were able to get a high peak at 11.6 centimeter. And I guess I am a bit, yeah. So, yeah. So it's the same graph, and we were able to get a high intensity and a high maxima at 11.6 centimeter. And there were other trends also, but they were less compared to the intensity that we were able to observe for 11.6 centimeters. So that's a great length. Now this is also a summary, and we were, clearly able to observe it's 11.4. It's a just correction. It's 11.4 to 11.6 centimeter length, and that coincides with the maxima of intensity in terms of variation in length. Now, in terms of variation diameter, you can clearly see that from the very horizontal at the bottom axis, 2.5 millimeter and 2.95 millimeter have no, glow, not a very high glow as compared to the 0.5 and 0.7 millimeter. They have a very, drastic glow. I mean, not drastic increase in glow. So that is what I mean, and clearly see that 0.7 millimeter has a higher intensity as compared to even the other three, the 0.5, 2.59, 2. So that's the optimum, I will say the best diameter for our experiments. And I will just go through these videos to show you the clear effect in terms of intensity. Now this is 0.7. I'm just going, I can move towards these while we are discussing if you have any questions about these. But you can see that this has a very low intensity, 2.95, but 0.7 and 0.5 have a very high intensity. So these were the results, and this is also evident from this summary here that 0.7 mm has a higher maximum intensity, but the glow time is very much less, and 2.95 has a higher glow. So energy efficiency. Now, in terms of energy efficiency, I will break down the energy efficiency into two parts, since they are opposite ends to the problems. For the brightest part, we had the least glow, and for the maximum glow, we had a very low density, very low intensity, low brightness. So I will distribute the energy efficiency part into two regions: brightness of the lamp and the long-running steady glow of lamp. And just to include the variation part as well, the efficiency versus length, you can clearly see that 11.4, this point is 11.4 centimeter. This coincides with the maximum efficiency of the lamp since it had a higher glow, and this 0.7 millimeter has a higher efficiency in terms of diameter. So as evident from the previous results that I already mentioned. Okay, so just to conclude and to move towards a summary, that we have the brightest graphite lamp at type HP, the length 11.6 centimeter and diameter 0.7 millimeter. This is the conclusion. The results that I just pointing out to in the graphs, this is the conclusion for all those results. And the long running graphite lamp would be with type 2H, HP, and 2B. I've added the other two as well, since they had a more steady glow, a long running glow, but they had a less brighter glow as compared to the previous case that I mentioned. And then the length optimal would be, for this case, will be 9.6 to 11.6 centimeter, and diameter would be 2.95 millimeter. Now, increasing efficiency, further increasing this efficiency, we can use inert gases and vacuum sealed jars so that you can enclose the whole process inside in a vacuum, so that it doesn't interact with the oxygen and the other environmental conditions. And then we can also include the optimum resistance and a temperature part inside this whole setup, and then we can find that particular resistance and temperature, and then that can move towards increasing this efficiency of the lamp. Now, improvements can be the optimization of the lamp, just on the lines of what I mentioned, finding the optimal limit for the resistance and temperature, and use of better quality pencil rods, and then involving temperature dependence as well. That's it from my side. Thank you so much, and I'm looking forward to any clarification questions that you want to ask.
Hello. Okay, I'm Annalise. I'm gonna propose graphite lamp, and well, my slide sharing. Okay. So the problem states to devise the most energy efficient lamp possible using graphite rod of a pencil, and investigate how the intensity and duration of the light depends on the hardness of the graphite and other relevant parameters. So let's go back to the presentation and put some good and weak points. The good points are that they made a good variation of the set parameters, varying the hardness and the length of the graphite rods. They did a lot of experiments, and they determined the best combination for the setup with the duration and intensity of the light emission. So the weak point we discussed was that the spectral response of the photodetector was a bit ignored, and the temperature dependence of the resistance that is very significant for the graphite was we felt it lacks explanation. We felt that there was a lack of theoretical model, especially about black body emission, that is a very important basis for this phenomenon. And it didn't explain about the optimal parameters found. It was very fine to see what is the optimal parameters, but I don't see why this setup is the best. Actually, I felt lack of uncertainty in measurements, and it didn't discuss the emissions. Okay, so the points to discuss. Oh my God, my slides are not going forward, but I will say two. The points to discuss. I think I think we need a theoretical model. Oh, here it is. And to explain how is the light emitted, and why are the optimal parameters optimal, like I said before. I think we should explain more about the uncertainties of the measurement, and we want to see what are the points of optimization that were not measured of the impact. I think that's it. I'll hope we can start the discussion, and that we can.
I guess let's start with the first part where you particularly mentioned, I guess, that why is the light emitted? I guess that was your first point on the discussion slide.
Yeah.
So that phenomena basically is the light emission process. Since, as you know, as I mentioned, the main basic phenomena behind this whole process is Joule heating. So when a large amount of current passes through the conductor or the pencil, or in this our case, it results in high amount of heat being generated within that rod due to the high amount of resistance being faced by that current. So with that, that results in such a high amount of heat, and that heat then results in a emission spectrum, and that gives us the whole that particular glow of the lamp that as if, for example, if you can compare it with the normal lamp that we use in that particular format, that such a high glow is unique characteristic, since it's basically, if I just move towards the light bulb part, it has a tungsten filament, and that it heats up to a very high amount of heat, and then that it's related with the emission spectrum, and that it results in the why is that particular light emitted or we observe a glow.
Yeah, sure. I see. I just think you could have explored more the physics behind it, and should like explain more the equations and the phenomena, the physical basis, like you said right now in your presentation, and should like motivate a bit more.
Sorry, I'm extremely sorry to interrupt you. But I mentioned this particularly at the start of my slide, but since it was I had to move towards the investigation part, so I did not utilize spend more time in that particular part, and move towards the important conclusive results that we want us to investigate. But definitely I mentioned this in the slide, and hopefully you may have By asking this in the discussion part, you may have got my answer.
Okay, that's okay. And something I want to discuss a bit more. I found very interesting. You presented a lot of experiments, and you found the best setup for the glow and the glow time and the intensity. But I don't see why to expect that like HP will be the best hardness
I got your
parameter.
question.
And okay.
Yeah. So if, for example, I can explain this from this particular graph as well, or I guess I should explain this from from the resistance part. That's much more explanatory. So since I mentioned before that this whole glowing effect or that high amount of heat, it's related to the resistance part. It's either related to the resistance part or the current part. As I mentioned, because these were the parameters that are related to the intensity and the Joule heating effect, the huge amount of heat being generated. So that is then related within resistance. So that's something that we can conclude and that we both agree on. So in terms of hardness, this is the graph that we were, we measured these resistances, and for HP, we had the highest resistance. So if you want to, clearly discuss the physics behind as to why we were able to, get the high intensity as visible in this particular graph, it's because of that high resistance. It's due to that high resistance. And you may say that since the hardness is being increased, I should, get more glow for the versions of the pencil type for which I have a higher hardness, I have a higher resistance. But for that, the issue is that higher resistance, it restricts the current to flow. So that also results in some issues. But the point is that since you can clearly see from the resistance here that we were not able to get that optimum resistance, and that resulted in a less glow for those particular cases. So I mean, if I can just conclude this whole point is that it's dependent on resistance. So I had a high resistance for HP, and that coincided with my best pencil type for HP.
Okay,
now
let's
move on.
Let
me tell that for this moment we can add team members to the discussion, and then members to participate.
Thank you. I just want to say that I found this discussion is very interesting, but I thought it would be more like physically modeled in the problem, and found it would be more interesting if we had some equations to explain this phenomenon. And I found a lack of explanations in the efficiency part. You showed us the graph, and it was very nice. But how does this obtained except the experimental observations? Like, can you compare with some expected numbers, and can you explain more of that?
If I can just move towards my
about that
efficiency graphs, I guess.
Yep,
here they are. So
I think it's
okay.
25.
So for example, so for the length part, for example, if you refer to the first curve, I mentioned that efficiency is output over input. I was using the basic definition of output over input, and the output power, or the output that I'm considering for this part, is that effective glow, because the heat part isn't the optimal required output or the useful output. The useful output is the glow, because we are talking about the efficiency of the glow of the lamp. So that intensity was being, as I mentioned, it was, measured with the silicon photodetector, and the input power was being supplied by the DC power supply, and I had those particular readings. I've mentioned them as part of my setup image where I inserted those images, and that resulted in this beautiful curve that we have here. So I guess if you still have any questions, I'm here to answer.
Yeah, I think Carol and Felipe wants to add something up.
Yeah, just first on the problem of efficiency, right? So these are, you have this set of data which you extracted from with the setup you showed, but you couldn't make any predictions for what the efficiency should be, right? Because for instance, you optimize, for instance, length and the composition, and I noticed that you identified a maximum of either intensity or light duration for a specific length, right? If you can go back a few slides. Do you have any explanation for that? Do you know why that's the case? because I mean,
are you mentioning
go back a little bit.
This particular slide?
Yeah, maybe no, before, still before.
This
yeah,
one?
that's it. That's it.
Yeah, sure.
No, the one which have many lines for different lengths.
Many lines for different lengths. This one?
Yeah, that's it. That's it. 18,
okay, sure.
Yes. So, for instance, there you identified that 11.6 centimeters has the highest light intensity. Do you have any idea why that's the case?
I just answered. I guess your fellow team member. She just asked me this particular question as to why I concluded that this is the particular optimum, glow for my experiment. So as I mentioned, that this is dependent on the resistance, and I can clearly observe from the curves that this is, this curve has a higher trend above the rest of the trends that are for the rest of the lengths available on the graph. So this clearly shows that it has a higher intensity and it remains at the top of the curve. Now, the physics behind all is this phenomenon. As I mentioned before, it's related to the resistance at that particular length. And I mentioned that that resistance, is very much higher as compared to the remaining lengths. So,
so it's best to increase resistance. Is that the case?
Yeah, I can just show you. If I think I haven't shown you the length graph, you can see that this 11.6 centimeter length has a higher resistance. Now, you can see that I was able to, measure resistance for the other curve points as well, but the experimental results clearly showed that the maxima, it lies at 11.4 or 11.6. That's the main region where the maxima lies.
But doesn't your graph show that you have even?
I'm extremely sorry.
Go on.
May I? I'm wondering that your resistance is very important, but your source is a voltage. You have only one voltage. So if the graphite changes the resistance in time, you have changing of current. So you think the current is important to obtain the best combination of length and hardness.
That's the best combination is on my experimental results, but you can clearly see if I can move towards this. For example, let's take this route. So that current is kept constant after the particular maxima, right? So
I'm wondering that if you have a fixed voltage, if you have different resistance, you have different currents. So do you have actually different power dissipation in your graphite? So I'm wondering, in fact, the 8B is the best one, but you haven't achieved the best current to this problem to have the HB glowing too. That's my question.
And we need for it very short answer, and it's gonna be the last one. Okay. Yeah, please, reporter.
Oh, okay, thank you.
Yeah, very short answer.
I just wanted clarify this question because I assume that she's asking that why keeping the voltage constant and then what's the dependence of the resistance and the current for that pencil rod? Is this the question?
No, your source is voltage fixed. So you have one current for one resistance. So so maybe for the HB you never achieve the best current to blow the HB graphite.
No. Okay, let me explain my experimental process. I guess that will clarify things. So this basic thing is that for performing experiments, we always have to keep a single parameter constant. So if I pick up a particular pencil rod and then I perform experiments, so I change the current while keeping the voltage constant, and that current it resulted in a transient time and the steady time. But that particularly, I guess that can show. I mean, what I was trying to conclude here, that this is a particular observation that we were able to observe in this whole process. That main observation is that as the maxima is reached, After that, the current is constant. It's set, it's at a particular value from the DC power supply. But you can clearly observe that the intensity is decreasing. So that coincides with the decrease in voltage on the power supply, since it's, you know, dependent on the, it's being measured across the pencil rod. So this is something that we observed. I guess this will be a, I guess this is what we were asking for in particular. I hope I've answered your question.
Excellent. Yeah, I think we've managed to show for you everything with intelligence. Thank you very much. Thank you, opponents. We desperately need to stop the discussion at this point because we're out of time. Opponent, your concluding remarks, very short, please.
Okay, sure. Okay, so I mean, I worked on, you know, I performed great experiments, I varied the experiments, and I think I was able to, you know, move towards the conclusion part as what the problem statement required. Now, in terms of the discussion with the opponent team, it was a great discussion, and they definitely, you know, included, mentioned some of my, you know, weak points that I should, you know, use to improve my solution of the problem, the temperature dependence part. And I guess they, you know, we had a very great discussion on some of the parameters, and they, I hope I've answered their questions as well. And I think we are, you know, at a place that I think we can conclude that our understanding of this particular problem is at a certain level, and we agree to some of the most, you know, conclusive results of this particular problem. So that's it. It was great having discussion with Team Brazil on this particular problem. Thank you.
Yes, thank you, dear Chairman. I have plenty of questions to this presentation, but I'll try to somehow keep myself to most important ones. So first of all, could you please tell me what is the definition of efficiency? In your case, it's kind of, there are too many ways to define efficiency from the beginning. And could you please show the slide where you have the definition? Because it's dimensionless, which means that you divide something over something with the same units. So what is efficiency? It's a question to the reporter, of course.
Yeah, sure.
I think you need to share your slides.
Yeah, I'm sharing my slides as well. Wait a second. Oops. This. Okay, now in terms of what I interpreted or what I mean by the efficiency part is that I have to, you know, get the useful output. I have to get the maximum glow for a longer period of time from this whole lamp. So that will be my higher efficiency, or that will be the highest efficiency for this particular lamp. For example, if it has a higher peak, if it has a higher glow, and it has a glow for a longer period of time. So that is my definition for what I mean that a higher efficiency lamp would be.
No, it doesn't. Sorry, I have to interrupt you. You have a slide showing efficiency versus length or versus diameter. Yes, this one. So you have efficiency on y-axis, and it's calibrated somehow. You have 0.6 efficiency. What does it mean? Efficiency equal to 0.6.
Yeah, just tell us how you calculated it.
Yeah, I'm going towards that part. As I mentioned that the initial settings for the input power were in voltage and amperes. I will be talking in terms of units now. So that's the input power. So I have to, you know, divide output power over input power. Now the power is, you know, it's related with intensity over the into surface area. Now the intensity that I was being I calculated from the lamp, I used that, I multiplied it with the surface area of the rod. It's the outer surface, cylindrical surface of the rod, and that I used, and that for that particular rod, that result gave me the output power. It has a, you know, proportionality there, and then when I divided that, you know, gave me this particular result in terms of the efficiency.
So intensity is okay. Never mind. I got your answer. Now, slide number 16, or should I? Okay, can I ask another question?
You're still only rising 10%.
Yeah, okay. Slide, we can stop at this one. Yes. So how do you explain the decrease of intensity? Repeat it again. The current is constant in this experiment. Is it correct?
I missed your last point. Can you repeat?
So intensity versus time as a function of time is decreasing.
Yep.
And the current is constant. Is that correct? You are sure the current is constant?
Yes,
like
the current remains constant after the maxima. If you can see my mouse cursor, after this particular point, the current remains constant.
Then how do you explain the decrease of intensity? It's kind of really trivial.
Yep. So as I mentioned while discussing with the opponent team as well, that this particular intensity decrease, it coincides with the decrease in voltage, because we were, measuring the voltage levels at each instant. And that, for example, if I just kept the constant, the voltage will be decreasing, and the resistance, since it's a direct relationship, so it will have an impact on the resistance as well. And since I mentioned that intensity is it's directly proportional to the resistance, so that will have an impact. Now the second point is here that's worth mentioning is that as we move towards the end of the point, as we move to the higher glow time, the graphite content is decreasing, since it's at a higher temperature, and that we can it's my assumption that it's being converted, the carbon content is being decreased, so the conductivity and that whole graphite content, since that's decreasing, because we were able to observe. I think if I can show you.
No. Okay,
No.
I think we don't have time for that. So resistance of the rod goes down.
Can I add something?
Okay, I have no more questions.
Wait.
Can I add something to this?
There is opponents who want to add something to the discussion of intensity, if it's really needed.
Yes,
okay.
Anna, please.
Thank you. So the decrease, the lower intensity, the decrease of the intensity is due to the change of the resistance with the temperature, and actually the graphite may burn and change the composition. So this is very untrivial, as you said, and it's very interesting to investigate. But the change in the resistance are the major point here, I think.
The resistance goes down with time. That's what we conclude from this graph, and this is untrivial, as you point out, and we don't have an explanation for that. This is
Can I
thank you, opponent?
I mean, I wasn't able to raise hand because I'm co-chair. Sorry.
Okay.
So yeah, please, reporter team, can you tell me is your response of your photodetectors that you use is equal for all wavelengths or not? In your opinion?
No, I guess we.
Yes or no?
No, we do not, check this particular responsivity thing for our photo detector.
Yeah, but on your opinion, just make educated guess.
I mean, you want.
Do you think it's very with wavelengths or not?
Do you want a theoretical explanation or what? Or are you referring to my experimental results?
Your theoretical answer, yes or not?
No. No, my answer is no. That
it doesn't change. Okay. And another question: do you think that spectral properties of emission of your rod change with your intensity?
I'm extremely sorry. Can you repeat the question?
Does the spectral properties of emission of pencil rod change with its absolute intensity? The spectral properties of this emission change with absolute intensity?
Yes.
Okay. And then for opponent team, what do you think about photodetectors? How do they usually work? Do they depend on wavelengths or not? Yeah, please.
Can I respond?
Yeah. Opponent team can do.
Okay, go on.
In general, silicon photodetectors have a response closer to the visible spectrum, and they probably don't detect a lot of infrared radiation, which is probably an issue when you're changing the average temperature of a graphite. So you're probably change in the peak at which your photodetector is able to detect and the peak of the emission of the graphite itself. So photodetectors usually have a response that falls off.
Oh, okay. Yeah. Thank you. Thank you.
Excellent, excellent. Dmitro, you still have your hand raised. Do you want to ask?
One very quick question. At the slide, it seems like you're measuring resistance. How exactly is resistance at zero length 5 ohms? Slide 15. Yeah, so at zero length, the average resistance is 5 ohms. Why is that?
I mean, it shouldn't be the case because obviously at zero length we have no particular graphite rod in between, so it should not have any resistance. But I guess there is an intercept, and an explanation for this intercept can be, I guess, in terms of the external conditions being applied, since we know that resistance is also dependent on temperature as well. As I mentioned, mathematical point as well, that there is a dependence of resistance with temperature, and I wasn't able to investigate that because I mentioned that in my limitations part, and that's what it was pointed out by the opponents as well. So I think that could be a reason for this intercept. I mean, it should go towards zero.
Okay, thanks.
Thank you. Ricardo, if you have any short questions, please make it as short as possible.
So how did you measure resistance? Just once again.
No, now I wanted to hand it over to Ricardo.
What was your question? Because there was some many people were talking.
Yeah, that's me. So
Yes.
Do the graphite rods break? Or, yes, it's a rhetorical question. Have you estimated, like, I don't know, reasons because of this?
Yes, we were able to observe the breaking of the graphite rod at a very low diameter for the 0.5 millimeter case specifically. And we were also able to, observe this particular point. I mean, it's something when, we were in the transient stage. If at that particular point, if you, just vary the current very, quickly, then that can also result in, a short explosion of those graphite rod. That's an observation. I may think that's in it can be improved with further experiments or something, but for major point with that, I think it's because of that small thin density of the graphite. It's with the smaller diameter. That's the clear point where we were able to observe the breaking of the graphite rod.
Thank you.
Right, but not every pencil broke. So
no, if we steadily increase the current to the maximum current, we are able to find the breaking point.
Thank you.